is the rock that I hit with the hammer yesterday. And what you can do do a similar process to the tar sands, and you can kind of heat it up and crush it. And in that process, you can get the oil out. And you saw yesterday that I had to sort of break it down for you to be able to smell that oil. But it's definitely in there, right? So it has that kerogen, but it's not liquefied and beautiful like normal petroleum. Methane hydrates, this is something that we could possibly go into in the future. They're basically like little stone-looking pieces of frozen methane on the bottom of the ocean. But if we were to go mine those out, we would disturb the benthic environment, and we could put a bunch of methane into the atmosphere, which is a bad idea because it's more powerful as a greenhouse gas. So we talked about types of coal mining already. You have surface, strip mining, right? Mountaintop removal, those are surface. And then you have the subsurface mining with like room and pillar and stuff like that. The oil sands, the thing about the oil sands that makes them particularly bad is that you have to strip mine them just like you strip mine coal. So you're going to have the complete habitat devastation, right? But then on top of it, you're also going to have to use a lot of fresh water to help chemically process it to get the oil out. So it's as environmentally destructive as coal as far as habitat loss, but then you're going to have this added problem of you having to put energy into it to refine it, and then also you're going to use a lot of fresh water. So it makes 3 times as much polluted water as oil. So you have this byproduct, and that can cause groundwater contamination if it gets into the aquifer. So that's the problem with tar sands. Like, I'm really excited and happy that the Keystone XL didn't get passed. Like, this is the worst way we could possibly get energy. It's not that efficient. So anyway, how much we actually have versus how much we can get out of the ground are 2 different things. Proven recoverable reserve is what we can make a profit on, right? Like, because of marginal cost, you can't go every single drop of oil ever on the earth, right? So you can only get so much. And that amount, where we're limited by technology and monetary things, that's the proven recoverable reserve. And over time, as technology gets better, that proven recoverable reserve does get more because we have the technology to get more out of the ground. And so we've definitely done that with oil. There's primary and secondary extraction that we used to go and get a little bit more out. Did we do this yesterday with the distillation of oil? So this is what it actually kind of looks like. I'll kind of zoom in on it a little bit. So what you do is you boil or distill that crude oil. And so the things with the higher boiling points, they get fractionated off right here. And so the higher you go up here, the lower the boiling point. And so basically, this little chamber is really hot down here, and it gets cooler as you go up here. And so those things condense. They liquefy back after you boil them at the right temperature, and they get pulled off. That's fractionalization. After we fractionalize it, like the gasoline, for example, it condenses anywhere from 20 to 200 degrees Celsius. After you pull that off, and once you get it ready for market, that's called refining. So an oil refinery is where they make your gasoline or your whatever. But so that's the 3 different processes. But about half of crude oil, 48.5%, about half of it does turn into actual gas that you can put in your car. But you know, we have diesel and jet fuel and all this other stuff. Not every drop of oil makes a drop of gasoline. It's only about half, right? So that's pretty interesting. Did you think that you just like drill for oil and then you do something and then it's gas, right? That's what you thought? But gas is just like one of the hundreds of hydrocarbons that are in oil. So you have to do quite a bit to it. And so like I said, refining, like I said, that's where you go in and you separate them and then you get them ready for market. So after they're fractionated, fractionalized, part it both ways, you refine it and that gets it ready for market. So anyway, stuff like tar and asphalt, that comes from oil. So anyway, how to make electricity. Any of these ways that we're going to be talking about electricity, most of them, other than like photovoltaic cells for like solar power, what you're going to do is you're going to take something and you're going to heat it up. So in this case, this is how plant blowing works. You're going to take that coal, and if you crush it and pulverize it, it increases surface area, so it's going to burn faster. Just like if you have a sugar cube and then you crush it up, it dissolves faster in the water. Same kind of idea. Anyway, so we're going to crush that coal up and we're going to burn it. And that in the furnace here, we're going to have a pipe of water come through this, and it's going to get hot. And I don't know if you have a granny that's ever made like a pot roast in a pressure cooker. Y'all have that granny like that? You have a granny? Do you have a pressure cooker? I have both. Okay. So anyway, if you have a pressure cooker, like the way that works, have you ever seen like the steam comes out and it can burn you and all that? It's kind of scary. Well, what a pressure cooker does is it keeps the pressure inside of that pressure cooker, inside of that pot. It keeps it way higher than the pressure of just normal atmospheric pressure. And so what ends up happening, at normal atmospheric pressure, I could take water and I could put it on a hot plate and I'd cook it all day long, as hot as I could possibly get it, and it will never get above 100 degrees. At normal atmospheric pressure, water cannot get above 100 degrees. Because if it's above 100 degrees, guess what it is? Steam. And it's water vapor. Okay? And so people don't get that. I wish I could have like a hot plate and I'll show you. But take chemistry with me and I'll show you then. So anyway, that's a chemistry thing. But in a pressure cooker or in this pressurized pipe up here when we're trying to make electricity, they increase the pressure, and so the temperature of the water can get way above 100, 200-300 degrees. But it's only because it's pressurized. So they let it get super hot, and then when they're ready to make the steam, they release the pressure, and then that steam will turn that turbine. So anyway, this is your little pressurized pipe right here. They release the pressure, steam turns the turbine, and then inside the generator there's little magic fairies that make electricity. No, I'm kidding. But do you know how electricity comes from a generator? Do you know what actually goes on inside of a generator? It's like the turbine turns the generator and you make electricity. Do you know what goes on inside of a generator? Do you? Anybody? There's a magnet. Okay, that's right. And so let me try to draw it for you. So there's two ways. Well, there's probably more than two ways. But I'll tell you two ways to go about this. So what you have inside of this generator, you have a coil of wire. So I'll do a different color. The wire is not red, but there's a coil of wire, like a cylinder. And then the magnet goes in and out of that coil wire, and that starts electrical charge. And so, like, electricity is a flow of electrons. And so that's what's happening. Like, there is a magnet and a coil of wire, and you can either take the coil of wire and spin it around the magnet, or you can take the magnet and move it in and out of the wire. But basically, you got a moving wire, magnet, paired together. And so that starts the electrons flowing in that wire, because metals have electrons that can flow, and that's where your electricity comes from. So I always think it's funny, like, oh, it turns a turbine, blah, blah. But then what, right? So anyway, here separately, you have a cooling loop and what's happening in the cooling loop. If you ever go to Plant Bowen, like inside of this big thing, this big concrete cooling tower, there's just like water, and it drips down the side like a waterfall, and it's just really cool and like beautiful and neat. But like out of this, when you see the smoke coming out of this, it's not smoke, it's just steam. So like this is just water vapor, whatever, that doesn't affect us, because water vapor is already an abundant, important greenhouse gas. As far as like carbon emissions and the sulfur and all that, that's your smokestack. These are the really tall pipes. And the reason they're really tall is because they have to overcome inversion layers, and so that's the thing. But that's where the carbon dioxide and the sulfur and all that, that's where it comes out, this smokestack. So this is the yucky one, right? And remember, this is where we put the scrubbers to remove the sulfur dioxide, so the acid rain has gone down because of the 1990 Clean Air Act and the sulfur trading. I just reviewed like everything we ever learned right there. Did you get it? And
the reason they're so tied to the inversion thing was because of the mountains in Las Vegas.
Yeah.
Nevada.
Were they like super tall out there? So yeah, people like smart people, when they engineer these things, like they think about the climate. That, I mean, it's a lot that goes into this. But they can be taller or shorter depending on where they are. So anyway, if you look at as far as production and consumption of coal, we China bakes and uses the most. We still have the most. Like having the most, it'd be kind of like the largest reserve would be like, I have the most money in the bank. Well, if you're not spending and buying a lot, like that's the production and consumption that I'm talking about. So China has, they have a lot, but we have the most. But they use the most because they're making all of our crap, and they have like 3 times as many people. Okay. So and then we come after that. Australia's up on in there. But as far as who has the most, remember did I tell you yesterday the United States has the most coal, Saudi Arabia has the most oil, and then Russia has the most natural gas. But you can see like we're pretty close to the top in all this. And we actually produce quite a bit of oil. Like we produce 8.8% of the world's oil, and Saudi Arabia is only at 13%. But it's just that we use so much, right? Our production is good. We have a pretty good supply, but it's not enough to meet our demand. So there's that. So liquefied natural gas. The thing about natural gas, it's kind of seen as like this bridge between fossil fuels and cleaner alternative sources of energy. Natural gas makes about half as much CO2 for each unit of energy. And so it burns a little bit cleaner, so you don't get as much of the greenhouse gases. How it's extracted with fracking and stuff is kind of crazy and scary. But once you get the product, it, like I said, it can be seen as bridge fuel because it emits less carbon. And so people see this as a way to get us to solar and wind and things like that from more oil and coal. So oil isn't everything. I think you already knew that. Anything that's made of plastic is made of oil. And everybody's like, well, everything causes cancer. The reason everything causes cancer is because oil has a lot of cancer-causing chemicals in it, and you have put more cancer-causing chemicals in it, carcinogens in it, to make it clear and hard from black jello. Let that soak in, right? And so all the things like BPA, that's it helps it be a resin, like it helps it be like a hard piece of plastic from oil. And so yeah, that's most of the reason why everything causes cancer. Everybody says that. If you look at this little picture right here, what this is showing is that the United States, we peaked in our oil production around 1970. And so if you look at other places like Russia peaked a little later, and then it looks like other places of oil, places like Argentina, Venezuela, places in Africa, they have a good amount of oil. Africa has like all the natural resources you could ever want. They don't have any food, but it's not funny. There's the Middle East, heavy oil, and then you see natural gas and then polar oil. So it's kind of like, this is just a beautiful example of marginal cost. We took what was easy to get to, and then we're starting to scrounge around looking under the couch for coins. Like, that's what we're doing right now, okay? So we're broke, and the peak global oil production, depending on where you look, what part of the world, and what scientist you are, it's already peaked or it's peaking right now, basically. So that's kind of scary. We have about 50 years left worth of petroleum. So by the time you die, we'll run out of oil. That's terrifying, right? Or just kidding. We're just like past that Keystone we'll pass that Keystone pipeline thing, and then we'll use those oil sands from Alberta. That's what will actually happen, right? Like, we'll just start like crushing up stuff and ruining Canada because nobody lives there anyway. Just kidding. So Hubbard's peak, he talked about us peaking in oil production around 1970. I just showed you the chart of that. And then global oil production, he predicted 1995. And his prediction, though, like, he didn't take into account like increased technology and then also polar oil exploration. So we're peaking now, probably. Here's the thing. Talking about scrounging under the couch for every last little quarter is broke. And this is on the test tomorrow. So what ended up happening when we first started really drilling for oil, trying to put it in our cars, World War II, all that, we put in a little oil rig and you put in a well. And so I told you guys that natural gas is just made anytime you have anaerobic decomposition. It's not made in its own special place. It can be made with coal, oil, made in landfill, swamps, whatever. Anyway, so you have this cap of natural gas on top of the oil, and you just put your well down into the petroleum, and then you just pump it up. Make suction, and you pump it up, just like a straw. That's all it is. And so that's real easy. Not a lot of technology went into this. And so that's primary extraction. What's ended up happening, though, is a lot of these wells, they just pumped all the stuff out and then they moved on. And so wells that were closed in the 60s and 70s, because they pumped everything out with just normal pumping, they actually have gone back in and reopened them as the price of gas has come up. And so let me show you what secondary extraction looks like. With secondary extraction, what you do here is we know that oil is less dense in water, and oil will float on water, right? So if you take some seawater and you pump it down into your permeable like oil layer where your oil is, the oil will float to the top of the water, and so you can get more out. Isn't that very clever? Yeah. Or if you're not on the ocean, like not all oil rigs are in the ocean, right? You can just use steam or water. So anyway, and then now that natural gas is more profitable, they are starting to pump out the natural gas as well. So there's that. So this is secondary extraction. And like I said, a lot of old wells that were closed because they weren't profitable anymore, they actually went back in and opened them back up. So highlight primary and secondary extraction. Those are really important. No matter what we do, we can't get every drop of oil out, but we can get a lot out. Fracking, this is what I was talking to you guys about a little bit with natural gas. This is a real big problem, especially for groundwater contamination. So what they do with fracking is they'll take and they will break rock open, like shale, like a rock with the oil in it. Well, sometimes it has natural gas in it, and they'll break it open. It's under the ground near aquifers, near drinking water. It's crazy. But they'll put pressurized water into the rock and they'll crack it open, and all the gas will come out. And natural gas, like gas. Like I can blue light, I'm burning like something on the stove gas, okay? And so then they'll pump that out, and there's tons of it, like underneath the shale that goes through New England and out west. I mean, there's like an ocean of natural gas, a bunch. But when you break that rock, that natural gas doesn't just go into the pump that you're taking the natural gas out of, it goes into the aquifer. And there's videos of people being able to light their water on fire. And I have a movie for that. We may get to watch a little bit of it, probably not, but maybe if we finish a little bit early, I want to show you at least what it looks like for the people that are having to deal with this. And then the fracking fluid, like I said, drinking water contamination is a big problem. The fracking fluid has like 500 chemicals in it, and several of them are known carcinogens. And so these people are getting sick, they're getting cancer, they're getting headaches, and they don't have clean drinking water, and they're having to sue the companies. We are kind of not, our bedrock here is not shale, and so we're kind of lucky in that regard. But fracking and the influx of natural gas into the market in the United States, because of this, that's the reason you're paying $1.80 for gas instead of $3. So it's good and bad. So anyway, that's what fracking kind of looks like. You, like I said, you have this well, and you put the pressurized fluid, fracking fluid, into the rock. It cracks it open, you get the natural gas out. And a lot of times, like I said, drinking water contamination is a problem. So natural gas, it is also, like I told you, it's in oil wells, right? And so the Deepwater Horizon, it had two problems. It should have never been open, like geologists said. It should have never been used. But it was a mile deep in the water, and so that made it really hard to clean up and stop. Because that was a huge engineering problem, right? To get a mile deep to fix something, that's crazy. And then also, it had so much natural gas, it was described as a well of natural gas with a drop of oil. And so they were just like trying to be super desperate and get every little bit out that they could. And so it took 86 days to plug because it was so far offshore, and also it had mostly natural gas coming out. So as far as like the oil spill, it got cleaned up pretty quick because the methane was most of the oil that you saw. But the bacteria that did end up decomposing everything, they sold the oxygen, right? So it's kind of a bummer. Methane is a greenhouse gas. Like I told you guys, oil sands make way more CO2 than conventional oil because you have to process them with heat and energy. Shale oil, like from the rock that I showed you yesterday, that's even more polluting because you have to really grind that up. Burning coal, so if you're a lady and you get pregnant, right, and you can't eat a swordfish, it's because we have coal-fired power plants. Like, that's crazy, but that's true. And so burning coal is where the mercury in the ocean comes from. And we had already talked about that with the bioaccumulation, how mercury is is fat soluble, so it stays in your fat cells forever. And if a big fish comes along and eats a little fish, and then a bigger fish eats that fish, once you get to the top of the food chain, that mercury concentration is really high. And so, like I said, ladies, if you find yourself with child one day, like, you can't eat really big fish because that mercury has magnified up the food chain. And biomagnification and bioaccumulation is actually in chapter 14, which I guess we'll be doing tomorrow. So anyway, pollutants, and we already talked about all the pollutants and acid rain. Like, we already did that. Like, the nitrogen oxides cause acid rain, the sulfur dioxide from coal causes acid rain. Like, that's something we already did. Clean coal, you can remove the sulfur dioxide or nitrogen oxides in the scrubbers. We've done a really good job with that. And so for me, from an environmental perspective, I feel like if we pass some kind of emissions trading like we did with sulfur and do it over time, and give incentive instead of punishment for fixing that, I feel like that's something that we could easily fix. It's just there's so many parties that are interested in keeping it like it is, but then there's all these people suffering from the consequences. And we're just in a nice little bubble of the world where we have a good food supply, so we're not super worried about it, right? So anyway, climate change is a thing. Gasification, you can actually convert coal. You can kind of crush it up real fine and add it to oxygen, and it can burn like a gas, and so it burns more efficiently. So there's ways to get more energy out of coal, but still at the end you're going to get CO2 and any other mercury, sulfur that you don't remove. Carbon capture and storage, sequestration. Like, this is cute, and it's still in research and development. Like, there's all these ideas of how you can pump CO2 down into aquifers and bedrock and holes and all this. I mean, that's fine, but if a crack in the rock is ever happens, the CO2 is less dense than the rock, and so it'll float up to the surface. But CO2 is more dense than air, and so it'll sit at the ground, and then the dude in this truck right here, he'll die from asphyxiation because he doesn't know that the air is filled up with carbon dioxide because it sits right at the ground. That happened in Africa near a volcano. There was a volcanic, there was an eruption, but this volcano released CO2, and like this whole village died. Like, everybody died because the CO2 sits at the surface. So guess how many people's tried to do this? 0. Because it will kill everybody, and you don't have a way to know, right? So, yeah, this is not a thing yet. But they like to say it's a thing to make it sound like, oh, we have a way to, we're in process of figuring out how to store carbon. So, yeah. The Keystone Pipeline, like I said, it didn't happen. It was a big mess. Another thing we had already talked about, the sulfur in coal that can make acid rain. Also, like when we talked about mining, it can cause acid mine drainage as the mining tailings, right, the tailings of stuff, the piles of stuff that's left over, the sulfur in the coal can react with water and oxygen and make sulfuric acid. And so then you have water bodies and soil becoming acidified, and then that could lead to leaching of minerals out of soil. Remember, acidic soil leaches minerals out. And then also, it can lower the pH of the water below the range of tolerance of aquatic organisms. Alright, so mountaintop removal is obviously habitat destruction. And then, yeah. So a lot of this is fast review. So, which is good. You have a final next week. There's a picture of strip mining, and it looks like some mountains are missing. So mountaintop removal. And yeah, that's total habitat destruction there. Directional welling. Oh, this is important. The thing about oil rigs, right? Like, you have a platform, and then you have your little rig. And so that doesn't take up that much room on the ground. But, and we think about coal mines, right? That's strip mining, and it makes a big mess, unless it's subsurface under the ground. But the thing about oil rigs is they still cause habitat destruction because you need roads for exploration. You need infrastructure for the people that work there. The ponds for the waste products, if it floods or leaks, it can contaminate the aquifer. And then, so you have all this habitat fragmentation. So that's on the test. Yes, the actual footprint of an oil rig is smaller than a coal mine, but you still have all this fragmentation for the infrastructure to get it there. So, directional welling is just where underneath the surface, instead of just having, it's pretty interesting. Like, you can have a well and you can pull the oil out from here, but then directional drilling could like pull out the oil from this way too. It can drill to the side. That's pretty neat, right? So, if you want to be an engineer and you want to make a lot of money, and just like chill out and retire, and instead of like helping the people on Earth, like you could totally be a petroleum geologist or petroleum engineer, you would make total bank, but then like lose your soul. No, I'm just kidding. Lucy, my owner, her brother is doing that. I taught him last year, and he's a really smart kid. Like, and he went out to I think he went to Wyoming to college because out west they have like all the mining and petroleum schools because that's where most of the minerals and stuff are. So when I told him he gets rich, he can come and give me some money. Are you listening out there, Nate? Give me some money. So anyway, yeah. Another thing we can do, we can totally go to other countries and take their stuff. And so profits from other countries when we go drilling. They actually, the problem with that, like I said, places in Africa along the Ivory Coast, they have tons of oil. Okay? But that money's going to the government and to the multinational companies. It's not going to the people that are already impoverished. They don't even, and they're having to deal with, no water, no electricity, all this stuff. And when these multinational companies go in and drill for oil in these countries that don't have regulations, they do not clean up after themselves, and they have the refineries right next to villages and the little kids. I can show you some sad videos if you want to see. It's really awful. So, anyway. OPEC, I don't know if you know what OPEC is. And in 1973, there was an oil embargo, which means that all the countries that, like, sent us oil, they were like, you know what, why don't we get together, and then we could control the price of oil, and then we could kind of screw over the United States. But that's basically what happened, because all these countries were competing against each other, trying to sell us their petroleum, but then they all got together and were just like, yeah, let's do that. And so they all got together and they started trying to control the price of oil, and then they kind of wanted to show us who was boss, and they didn't send us any. And so we didn't have any oil. And so that was the 1970s.
Good morning, Wildcats. Today we will conduct our testing for U.S. history and economics. Again, what I'm going to need everyone to do is to make sure you power down your mobile devices.
So anyway, political things, and then also social conflict in the Middle East, that really changes the price of oil a lot. And so any kind of volatile situation internationally makes people freak out, the price of oil goes up. Or a natural disaster like a hurricane, price of oil goes up. So that's what ends up happening. And there was a huge problem after Katrina, because that was flooding and a mess. I don't know which particular hurricane you're talking about, but that's definitely a problem. So here is a graph. This is on your test. And the thing about this graph shows production and consumption. And like I said, if you don't look at the red lines, we don't really produce that much less than Saudi Arabia, even though they're like the #1 producer. But the problem is this. This is how much we use over how much we actually make. So we have to fill in this gap by taking theirs and by taking this a little bit extra. Okay? And so Germany and Japan, like I told you guys, all the other developed countries are like all totally on board with getting rid of or having less CO2 emissions, but they don't have as much coal, oil, and natural gas as we do. So yeah, I mean, maybe we act like jerk faces, but we have a ton of coal, so they don't. They have no reason to not be like, hey, let's put in solar panels, even though we're like as cold as Canada. That's what Germany's the #1 leader in solar worldwide. But they don't have the resources that we have. So we have a little bit more at stake to not use what's under the ground. Yes, ma'am?
So do you think if like the ROI thing for us is really low,
yeah, and so when I was in geology class in college, he was from out west, my professor was. He was from, I think he was from Montana. But then, like, what he was talking about, if the ROI gets too low for petroleum extraction, like, we have a ton of oil shale and tar sands. We have a ton of it. So we'll just use that. That's what we'll do. Because the money to fund that and to subsidize that technology is there for the oil companies. The money to expand into alternatives isn't there. And so after that's all done, you know that the reason we use petroleum is because we killed all the whales, and then somebody figured out that it could light lamps with part of petroleum. And so the reason you buy a barrel of oil that's 42 gallons is because that's how big a barrel of whiskey was, and that's what they put it in when they figured, this guy in Pennsylvania figured it out. So after we killed all the whales, that's when we moved to petroleum, and when we do that, we'll move to something else. That's sad. I'm sorry.
That story. There's like a picture, but it tells it, and it's like a picture of a guy lighting like
yeah, so they just needed some lamps, oil lamp. What's the lamps? What?
They, the government installed a solar panel for every, I think it's 300 acres that you have in Texas.
Oh.
And it's for the wells that they generate. But they have what are they called, the windmills?
Yeah.
But
they have a lot of
said that the solar panels that the government installed, it was mandatory for them to install. Don't even
Yeah, the efficiency of solar panels is really low, but we have a lot of wind. I think wind's the best way for us to go personally. But
their windmills work so much better than their old windmills that have been there since forever. Works
Yeah.
much better
And
than
Texas
solar
has a
panels.
lot. When we get into that PowerPoint, like you'll see that. But I mean, you can see that other countries, other developed countries, they have a lot more reasons to want to go to alternatives. They don't have what we have. And so, I mean, we're not just jerks. We just have a huge amount of resources. And we had half of a country, or most of a country, where nobody lived. And we could just totally exploit that before we lived there. Germany, Japan, they're small. They're the size of Texas, California. You know, they're little. And so they have a lot of people, but they don't have just vast amounts of land with nothing going on. So we are in a different situation. But here you can see the volatile nature of the price of gasoline and how it can go up and down depending on what's going on with the world and the climate. Hurricanes get worse with climate change. But anyway, Canada with the tar sands, you know, they were friendly democratic neighbors, and so that we like the idea. Some people like the idea of using the tar sand, because, you know, they weren't gonna like use it to develop nuclear warheads and kill us and stuff like that. So like I said, there's a strategic petroleum reserve under Louisiana, and these like giant caverns, which is so interesting. My husband thinks it's like years worth, but then like it says like maybe a month or two worth. So there's the thing. ANWR, the Arctic National Wildlife Refuge, that's on the north slope of Alaska near the Arctic Ocean, like the top of Alaska, right? And so going back and forth and drilling there, I think they allowed, Shell, S-H-E-L-L, like the oil company, started drilling on the north slope, maybe near or in ANWR, and then they made them stop. Because with the water being so cold, if the oil did get spilled, you would just never be able to clean it up. And then half of the year it's frozen, so if you start cleaning it up, then you have to stop. And so they started, and this was like recent current event stuff, and then they quit again. And so I think that's good. But that's just a mess. Anyway, efficiency and conservation. There's a question on the test which is like, how could you be better at conserving energy or whatever? And so there's some easy things like insulate your house, use passive solar. I'm going to explain passive solar right here in a minute. And so a big one that you may not know about, this one's on the test, cogeneration. And so like, let's talk about like a power plant, like plant blowing, right? If they're using this heat to make electricity, there's going to be waste heat in the actual furnace. And so what you can do is they could heat maybe their own power plant, and then houses around it with that waste heat. And that would be called cogeneration, where you're heating buildings and surrounding areas, maybe other buildings, with the waste heat from the power plant. That's called cogeneration, which I don't know if they do that. That would be cool. But the thing is, like, Plant Bowen's already designed, it's already working, and you can't just like go back and be like, hey, let's do that now. You have to start stuff like this with new power plants. So it'll be hard to back engineer that without making a stall in production, right? So anyway, Energy Star appliances are good. They use less energy. Hybrid vehicles help. And you know how we talked about a minute ago how you make electricity by turning a turbine and then the turbine turns the generator, and in the generator you have a magnet or coil wires. Well, when your wheels on your car turn, right, if you take this little, is it drive shaft? Whatever. Yeah, okay, cool, I don't know. But while that's turning so your wheels can turn, right, if you take that rotation and you have a coil of wires and a magnet, you can make electricity, and that's what hybrids do. And so hybrids can store that extra electrical energy in a battery. Okay, and so it's pretty smart. Like, the internal combustion engine is so inefficient. Like, if you want a job to do when you grow up, come with a better way to have a car. And they already have hybrids and electric vehicles, but like, other than freaking light bulbs, like, internal combustion engines are about the most inefficient things ever. Like, and we don't have regular light bulbs anymore. Like, they have moved to almost everything's fluorescent now, and so you don't have that waste heat. That waste heat's just second law of thermodynamics gone crazy. So, CAFE standards. The CAFE standards stand for Corporate Average Fuel Efficiency, and so that's what the CAFE, that's where that's come from. And so what that means is if we take a whole line of vehicles like Toyota or Ford or Chevrolet, let's just pick the company, let's pick Ford, okay? Ford can have a giant, what's the Ford's giant land barge called? Like that big old thing. What is it? Expedition, is that the thing? Is that the thing?
Oh.
Like land barge? You know. Like your Escalade. You ever seen that funny little... Have you ever seen that video where the guy's talking about the snow in Atlanta? Okay. In the Escalade. This is so funny. Back up and fun. I'm sorry. I'm getting off track. So let's say take Ford, and Ford has their giant Expedition, which the fuel economy is pretty awful. And then they have like an Explorer, and then they have like Taurus, and they have like tiny little cars like Fiesta. Basically, what CAFE standards say, like let's say the CAFE standards for a line of vehicles is 25 miles a gallon. You got to average all of them together and get 25 miles a gallon. So you can have a land barge that holds 12 people, even though you're one rich white lady with like one kid taking them to soccer. Like you can totally have that, as long as that. Like you know much. Or you can have that as long as you have smaller cars that are more efficient, maybe electric cars or hybrids or just tiny little cars. As long as it all averages out to 25 miles an hour. And so that's what corporate average fuel economy or efficiency means. Okay. So that's how the CAFE standards work. So any company that makes cars, they can, as long as it averages out, they're fine. They can make the bigger cars and smaller cars and all that.
Do they have to do that with the trucks too?
Okay, so trucks for like commercial trucks, like I'm gonna go be a trucker, or it's like a diesel industrial kind of truck, that's not counted, but like F-150 is. So yeah, yes. So,
So, but they don't count the diesel trucks.
No, they don't
like
count.
F-250s and F-250s.
It depends on what they were sold for. If they were sold for commercial purposes, I don't think it's counted. So like you know how Fords come up with like those white ones that don't have nothing on them, and then I don't think that counts. Like my husband has one of those. So there's like a line there, and it has to do with like tow and power and this and that. But yeah.
Oh, so if you like just have it just to have it, then that's in that category.
It has to do with the actual vehicle. Like there's horsepower, and then there's like towing capacity and all this other stuff. So I could look it up, but I don't know the exact numbers. But there's like a fine line right there on trucks where if it's for personal use, it goes into this, and then if it's for commercial, it goes into the other. So that's a good question. Anyway, after the oil embargo, we freaked out. We were like, we don't have any oil, let's do something. And so right after 1973, we made huge gains in automobile efficiency. Like if your granny or just, you know, you got pimped out old, whatever, El Camino, like they get like 9 miles a gallon, right? But after the early 70s, they really started, fuel efficiency started going up. And if you think about old cars in the 60s and 70s, they were huge and like made out of real metal. And so now we have like all these plastic parts and they're smaller. But that was why. That's why we changed from that. You know, if you hit like an old car from 1972, like your car's gonna be totaled and they're gonna be totally fine. They're gonna have a scratch on their bumper. Anyway, we're now there's a 35 mile a gallon requirement by 2020. So I guess I need to get on that. And cars are becoming more efficient. But again, that's the corporate average. So all these cars like the Chevy Bolt, like that's making up for Silverado, right? And so they don't all have to be here, but just they have to average out to be there. And so that's why they're kind of coming out with this stuff. But gas right now is only $1.80. Is that how much it is? I hadn't really bought gas. I didn't pay attention. Shame on me. But if it was $3, $4 like it used to be, people want to buy those more efficient. But when it's cheap like this, people don't care. So cash for clunkers. I don't know if any of your family got in on this a couple years ago. They gave you money to put in your own cars and get a more fuel efficient car. So that was cool. Now look, here it is. 1973 oil embargo. Initial freak out, and then this is like, let's put a TV in the back of the headrest and heat the steering wheel. Like that's where technology went into, right? Let's give it some more horsepower, faster acceleration. And it wasn't until they passed a new requirement, I think in 2011, that they actually started coming up again. So in 2020, we got to be at, what, 35 miles a gallon? So I don't know what kind of cars will be coming out in the next couple of years, but it should be interesting, right? Or depending on who's in office, like it could get voted down and like not have to do. So anyway, they always change their minds. We pay 2 or 3 times less than Europeans for our gasoline because we don't tax gas that much and then we subsidize it. So it makes it seem cheap, but the costs are externalized to you as a taxpayer. You just don't see it when you go to the gas station. It comes out of your paycheck and you don't realize it. Yes, ma'am.
What about the gas prices in California?
So California is always going to be a little bit more progressive. Their environmental regulations are more strenuous, and so they have, because especially with like Los Angeles, they have that awful smog problem. And so, did your sister go to UCLA? So she's University of California at Los Angeles, right? And so she's in that valley. And so they have that smog problem, and so they have to run all these special blends of gasoline to reduce on the NO2 emissions. And so that's why her gas is more expensive. And then they do tax it more as well. And it's because California just has way more progressive environmental standards. And so they have the smog problem, and then they tax it more. So each state can tax the gas. But here in Georgia, if we start taxing gas more, everybody would be super mad, right? So, yeah, she lives in Los Angeles, so that they're trying to cut down on that nitrous oxide, or nitrogen oxides, really. So anyway, that's hard to do because you're still heating it up. Anyway, if you internalize the cost for everything in gas, it'd be like $13 a gallon. And then if you go to Europe, it's $8 or $9 a gallon. So we're supporting something that's so destructive, just so people will be happy and vote for people again. So who contains the most oil? That'd be Saudi Arabia, while the U.S. consumes the most. So that's C. Which energy source is versatile and emits the least CO2? So the least CO2 comes from natural gas per unit of energy, right? Which of the following describes the process of heavy machinery moving huge amounts of earth to exposed coal? That'd be strip mining, so A. Which of the following does not describe natural gas that was formed biogenically? Now, listen, biogenic is like swamp gas or like in a landfill. It's near the surface by life. All right. Thermogenic is heat and pressure formed with coal and oil. So not biogenically, that would be deep underground. All these other things, that's biogenic. It is estimated that we've already depleted about half of our global oil reserves, so 50%. All serious problems are here, but like the greatest environmental impact from emissions from fossil fuels is probably greenhouse gases, right? So the climate change thing. What is a major problem of oil shale and tar sands? All of those. They release greenhouse gases. They have more habitat destruction. They release pollution. Don't say stuff like that. Please don't say stuff like that. What is supported by this figure? Without new discoveries, peak oil will happen in 2020. And you can see the top of that graph in 2020. So, anyway, let's just stop and take a little break for about 5 minutes. All right, so if we look at the next chapter, it was about conventional energy alternatives. So these are like geothermal, biomass, and hydroelectric. And so these aren't fossil fuels. They're kind of what we're using right now in place of fossil fuels, if we're not using coal, oil, or natural gas. But they're not exactly the best alternative. And so we're going to go through these. So what ended up happening, there's been nuclear problems. Fukushima had a tsunami that caused a nuclear meltdown, and I'm going to explain to you what a nuclear meltdown actually is, because you probably don't know. It just sounds scary, right? But you don't know what it is, right? So, so people in Sweden, they started trying to phase it out, but then they weren't able to completely do that. But they still, they're doing better than we are. So, anyway, a couple of nuclear problems. Chernobyl was one in the Ukraine, and Fukushima was another one. Chernobyl was actually caused by some people that weren't fully trained, just kind of doing a test real quick on the power plant. Like they were, it was kind of totally their fault. This was because of a tsunami. So I don't feel bad about Fukushima. Chernobyl was completely avoidable, and they didn't tell anybody. They let the radiation leak out for like over a week. They didn't say anything. They were just like, "Shh, nobody knows." But like. It was actually people in Sweden that picked up the radiation. What ended up happening were these people, they were going into work, and when you work at a nuclear power plant, like they are constantly monitoring the level of radiation in the atmosphere, and everybody kept setting off the little alarm. And then they were like, "What's going on? Is our power plant leaking?" And then they figured it out. It was coming from their shoes, and then they figured out it was coming from the dirt outside, and they figured out there was somewhere else, not in their power plant, that was leaking radiation. And they followed it back. Y'all remember our friends, the Westerlies? Yeah, the Westerlies had taken, oh wait, that's going the wrong way. So, we have the polar moisture. This is making, now I want to get a map out and see where the winds are.
The equator's beneath the African.
Yeah, but we're at 30 degrees. We're not going to figure this out. We're going to come back to this. Anyway, people over here had figured it out, but I seems like this would be in the westerlies, though. But, it could still spread. Probably would have spread more this way, though. We'll look at the winds. We'll find the latitude here in a minute, but not right now. Okay. So anyway, people in Sweden had picked it up, and then the people at Chernobyl hadn't said anything. Like, they were putting the fire out, but they didn't tell like the rest of the world that they had a meltdown. So they didn't take care of that situation really well. But Chernobyl, really, and Fukushima, those were only the two big meltdowns that have ever happened. And there's like over 400 nuclear power plants. So it's really safe. It's actually safer than coal-fired power plants because so many like safety checkpoints have to go through. But people just see stuff like this and they think of like your kids are going to have fluorides and then everybody's going to die, and then they're really ill-informed. So anyway. Our economy, though, mostly fossil fuels. 2/3 of our electricity, over 80% of our energy comes from there. When I say energy, I'm talking about energy also for transportation, which is not included in electricity. So when I say energy versus electricity, electricity is just electricity versus can I drive a car on it? Am I using this to run a ship or something? Okay. So anyway, we have a mix of energy. If you look worldwide, though, and this is what I was talking about with energy versus electricity. Energy overall, we have oil, coal, and then natural gas. Oil is number one because of the transportation sector. Just electricity, coal obviously is going to be the best one for making electricity, followed by natural gas. And oil is really far down in electricity because we're going to use it to run our vehicles and our ships and stuff. The reason it's used for some electricity, though, places like the Middle East, they, of course, are going to burn oil to make electricity. They're not going to import oil, coal to burn there in the power plant when they got more oil than God, but they're just not going to do that, right? So, anyway, most developed and widely used conventional alternatives, like I said, are nuclear, hydro, electric, and biomass. They're better than fossil fuels, but they still have some downfalls. Bioenergy is about 10% of the world's energy. And that's not because people love the earth and trying to save the trees. That's because they're poor and they burn firewood to heat their house and make their dinner, right? So nuclear is about 6%, hydro's after that. And then nuclear and hydroelectric are pretty important for electricity production. They're big for that. But obviously we can't use them to drive a car or a ship, right? Can't like put a dam on a boat, which I actually be like, that might be a thing. But you know, you have that whole gravity working against you there. Anyway, as far as alternatives, they're biggest. They're way more than wind or solar, way more. France gets about 75% of its electricity from nuclear power. In comparison, about 20% of ours comes from nuclear power. And we do have nuclear in Georgia, and they're actually, Georgia Power's expanding Plant Vogtle, right? And so, opening up a new reactor. And this would definitely be something that would rise if we did have some kind of regulations against carbon dioxide. You would see a shift there if that was put through. And so it's free of air pollution. We don't have to worry about sulfur or carbon or nitrogen oxides. It doesn't have any of that. There's other problems, though, for sure. As far as who makes the most electricity from nuclear, we lead the pack, followed by France, then Japan, then Russia. And then you kind of keep on going down. This has a lot to do with population and energy use. We have a lot of people and we use a lot of energy, so that's why we're number one. France and Japan, they don't have the fossil fuel reserves like we do, so they don't have another choice. That's why they use so much. So here we go. I have actually like this cute little model where I'm going to show you how this works. And it's on this table. I love these little projects because like I teach with them, like they're actually helpful. This one was from last year. So kind of like you're in the bubble that I would like to be in. Alright, so this is uranium-235. Can you all see? If you can't see, please move. So this is uranium-235. This is where we start. These are the products, okay? These are what I start with. So I have a neutron, see my little neutron? And here's my uranium-235. This is a huge, huge atom, okay? And so it's very unstable. So all you have to do is if you take this neutron and you hit it, it will break up into krypton and barium. So these are the products, and notice how they're smaller and they're more stable. And so when they are formed, you get 3 neutrons. So you start this side, you start with uranium and neutron, and it breaks into krypton and barium, and you get 3 neutrons. Now, if you do the math real quick, I'll turn it this way. If you're making 3 neutrons for every 1 uranium you split, that would be able to bombard 3 uraniums, and then those would break off 3 each, and that would make 9 neutrons, and then 27 neutrons, and then 81 neutrons, and 243 neutrons, and then you all die. Okay? So, what we have to do in nuclear power plants and nuclear reactors is to absorb these extra neutrons so you don't have a chain reaction. When you make a bomb, like a nuclear bomb, it's the same fuel and the same process. But in a bomb, they don't absorb the extra neutrons, and then the chain reaction takes place, and then people die. In a nuclear power plant, you can actually use control rods to absorb these extra neutrons, and so you just have a nice controlled reaction where you can monitor it and keep it at the pace that you're looking for. So it's pretty interesting. Like I said, uranium-235 though, uranium-235 is actually the least abundant isotope. So uranium-238 is really abundant. So you go mining for uranium, you're going to get mostly uranium-238, which you can't use, and they're going to refine it, and they do that through, what is that called? There's a word for it, and Iran's always enriching. Yeah, Iran's always like talking about enriching your uranium to make nuclear weapons. Like that's what they're doing, and so when they get the technology to enrich uranium, they're always talking about on the news, and they're always like, oh, that's what they want. Iran doesn't need any nuclear power, but they're like, it's for energy. But so there's your neutrons, and then that's happens. Now, so this is fission, and it has an I in it, and I'll tell you about that. So let me go up here. So fission. The way I keep these straight, because it's easy to get them confused, the word fission has an I in it. And so this little I right here, it kind of looks like a 1, and so you start with one big atom, okay? And like I said, you take it and you hit it with 1 neutron, and you make 3 neutrons. And so it's these extra neutrons that we're going to have to absorb with a control rod if you get too many, okay? So barium and krypton, these things right here, they're still large radioactive isotopes. And so when I say isotope, they're still just barium and krypton. They just have extra neutrons. Anyway, so that's fission. And so when that large atom gets broken into smaller ones, that releases energy because in the nucleus of an atom, there's a strong nuclear force. And so when you break this stuff open, a lot of energy comes out. And that's as simple as I can make that chemistry for you. Anyway, so what I just showed you is how nuclear energy happens. Nuclear reactor, like I said, that is the little chamber where all this goes down. And fission, like I said, is where you take large atoms and you bombard them with neutrons and they break down. And then it generates a chain reaction that can be self-sustained. And like I said, you need to kind of slow that down. So this picture to me, when I first started teaching this class, I was like, well, I'm not going to teach that. This is crazy. But it's really not that complicated. But I definitely remember being intimidated by this picture. Did you find this picture to be intimidating? Or did you just totally get it? It was fine. Okay, it looks fine. So what ends up happening, let's start at the beginning. These little metal sticks right here, this guy, oh, I can't write on it because I haven't expanded. But this little guy, this little stick right here, those are your fuel rods. And so that's where your uranium-235 is, okay? And then all of this red right here, this is all sitting in a vat of water. And the reason you need the water is called a moderator. And if you're having a discussion, the moderator will chill everybody out and keep them good and nice, right? And so the moderator in a nuclear reactor is slowing down those neutrons. The neutrons that get popped off after it breaks down, they can't be going too fast. You need to keep them calm, okay? So the moderator slows down the neutrons that get released during the fission process. And these control rods, this guy right here, and here, and here, you can actually pull them up out of the water if you need some more neutrons, or you can put them back down in the water and they can soak up the extra ones to keep the reaction at the right pace for you. So that is the reactor core. Now, if we look at a bigger picture, that's all housed in a containment building. So if something did happen, that radioactive material would stay inside the containment building and it would be safe, right? And so there's all these safety checks. So let's look at the larger picture. That obviously is going to make heat. That's going to release energy, and it's going to heat up that water. Now notice right here, this water, and I can probably make this picture a little bit bigger. The water that is radioactive, that sits in there with the uranium, it never comes out of this loop. That water is not allowed to boil, and that water does not turn a turbine. The water that heats up and turns a turbine is in another loop. So this pipe and this little chamber of water, they touch each other, and it heats up some different water in this secondary loop. And you keep it under pressure until you're ready, and then you let it steam and turn a turbine, just like all the other. So everything's the same. You're heating up water, the steam turns a turbine, but you're heating up water, and in a coal-fired power plant, you just have, you know, that water that heats up is the water that boils and all that, but the water that heats up from the uranium is kept separate, and you don't want to release that into the atmosphere. So
What happens if something happens inside that container?
this containment building has like lead and concrete, and so it can hold it. With Chernobyl, the top of the containment building was blown off. And so radiation got into the atmosphere. And when radiation gets into the atmosphere, that's a meltdown.
It still has radiation too, doesn't it?
Yes. And Chernobyl's had a lot. So, yes, ma'am.
Wait, like, I thought they had to, like, pour a bunch of water on the reactor.
Are you talking about Fukushima?
Yeah.
All right, so let me tell you what happened with Fukushima. This has to be kept kind of at a certain temperature. And so you do need to cool it down. And this little secondary process right here is cooled by another process. And so this loop, the cooling loop at Fukushima, is ran by electricity. And the electricity stopped getting made, right? And so they didn't have any electricity coming to the building because that whole thing got flooded. So the generators that ran the cooling loop at Fukushima, they didn't get electricity, so it overheated. And so that's what happened at Fukushima. And then there were several of these little reactor cores, and I think maybe, I want to say 2 melted down. Not all of them, but a couple of them did. And so that was the issue there. Their backup generators got flooded because they were right on the ocean. They were right on the ocean. So, yeah, that's what happened there. With Chernobyl, I want to say, that's like a really long story, but I think with Chernobyl, they had pulled out the they had pulled out the control rods, and they were doing a test to see what would happen if, and it got out of control. And so this blew up. So it was, I mean, if I'm going to show you a picture in a minute, you can see the top of the building ain't even there anymore. So anyway, that's how that works. And so still you got that nice little concrete cooling tower, and that's cooling this, and that's making steam, and it's just kind of all working together to keep this in check at the right temperature and kind of nice and as relaxed as possible. So all these things I just explained to you might want to highlight them. Like I said, the control rod, they absorb the neutrons. The moderator slows the neutrons down. And so that keeps it from getting out of hand. Fission happens in the reactor core. That's in a nice vessel that can contain the radiation if it were to kind of get out of the little reactor core itself. Not all nations require containment buildings. We definitely do. So that's good to know. Those radioactive isotopes, so they're called radioisotopes. The one that you need for uranium is 235, and you need to know that. So the problem with the uranium-235 is it's not very abundant, and then it has a half-life of 700 million years. And it takes 10 half-lives I guess that should have a V in it. It takes 10 half-lives for radioactive materials to get down to a safe level because it's 50%, 25, 12.5, 6.25. And so after 10 half-lives, it's at a safe level. So if your half-life is 700 billion years and you need to go through 10 half-lives to be safe, that's 70 billion years you're going to have to wait. Did you get my math there? So this fuel, after it's exhausted, you have this radioactive material that's radioactive for 70 billion years. So that's the problem with nuclear. It's not that, it's going to melt down and then we're all going to die and all this. No, you don't have nowhere to put the waste. So 99% of uranium, like I said, is 238. And so you need 235, and so you enrich it. You enrich the uranium. And that's what's always talking about with Iran and the missile crisis and Well, that's different, but they're always trying to get a missile and shoot it at somebody, and they're being ridiculous, right? And there's always like sanctions from the UN on Iran because they're trying to enrich uranium. So it would be like less entertaining on the news if they were like, uranium's trying to get more uranium. I mean, Iran's trying to get more uranium-235. Like that wouldn't sound as fun. So it sounds better if you like enrich the uranium. So anyway, after a while, these little uranium pellets are put in the fuel rods. After a while, they are still radioactive and they still have uranium-235, but just not enough to be fuel. And so these spent rods, they're stored in like little vats of water in the power plants. So that's kind of scary. Anyway, nuclear power, as far as the benefits, it has no power, it has no emissions. It has no, there was no smokestack like in a coal-fired power plant. There's no sulfur, no nitrogen oxides, no carbon, no mercury, none of that. So there's less health risk from pollution because there's no air emissions. And it's safer. If you look at the risk factor for working at a coal-fired power plant and injury and death versus nuclear is way safer. It's just the data on that. Uranium mining is going to cause less land damage than coal mining because you need like little sticks of uranium that can be used for 5-6 years. And you don't have to replace it. So like with Plant Blowing, we have trains and trains and trains of coal coming in every day. But with a nuclear, you just buy it one time, and it lasts for a while. Now, drawbacks, the waste is radioactive. It's not just some kind of fly ash that you can pile up in the back. If they are targets for sabotage, if you think about it, if a bomb had been dropped on one or somebody tried to blow one up, that would be devastating. And we have 435 of them, so that's not a drawback. That's just a piece of data. This is fusion, and fusion is what happens in sun. And so fusion, the way I keep fusion straight from fission is the U has 2 sticks. Let me show you. So 1, 2. Yeah, that's good, right? So anyway, and you're fusing together 2 things. Now, that hydrogen, that deuterium, it has a mass of 2, and tritium has a mass of 3. So anyway, those things, that hydrogen right there, that's in ocean water. That's in ocean water. So all you have to do is have some ocean water, and you can make this happen. Now, problem is, with fusion, you know how many times we've done fusion on Earth, and it's the same way? Have you ever heard of the H-bomb? Yeah, so let me explain this. H-bomb comes from hydrogen, this. And so we made fusion work, and the way we did that is we set off an atomic bomb fueled by uranium, and that's the only way that we were able to get enough heat and pressure to fuse hydrogen. And then that made a H-bomb, and then it exploded, right? So we did this with the H-bomb, but like you have to set off an atomic bomb first, so you know what else. There are people working on this, because if we can make this happen, we could have like limitless energy just from ocean water. But the amount of heat and pressure that's needed, some scientists, like they're in like little groups and they're working in different countries, they've made this work for a second or 2. But the amount of heat and energy they had to put into it to only get it to work for just a little bit was more energy than they got out of it. So,
is that with the, like, accelerators? Or they, like,
so the particle accelerators, what they're doing there is they're trying to look inside of an atom and find like little quarks and all that stuff. And so they're trying to find like dark matter and crap like that. But the particle accelerators, that's for that. But this is inside of like a, it would be similar.
How do they, like, what do they do to make
that much heat and pressure. The way they're doing it is they're like in little reactor cores, almost kind of like how you have the nuclear power plant. It's like in that kind of vessel. What they're doing in there to get the heat and pressure, I don't really know. That's above my pay grade, but I can look it up for you. But I don't know what they're doing to get that. I'm sure some lasers are involved in some stuff. I would like to know. We can look it up if you have time. All right, so what are we gonna look up? The westerlies and how people are trying to make fusion work. All right, but
and the
water.
The water, the fire, the...
How people can light their water on fire.
oh yeah, okay, got it. All right, y'all keep track, okay? Anyway, I don't know if you were planning on learning about the theory of relativity today. Do y'all actually know what that means? Like other than Einstein did it? You want me to explain this?
Yeah.
All right, Dane, show me what this is. Go for it.
Well, the only thing I know about it's like you requires an infinite amount of energy to reach the speed of light. Is the only thing I know about that.
Okay. Anybody else? So let me explain it to you. Energy is equal to mass times the speed of light. And the speed of light is a lot, right? And depending on if you're looking at like meters or miles, I actually have it on my AP chemistry formula sheet, I think. And two, it's 300 million meters per second. 300 million meters per second. So that's pretty fast. Yeah, take AP chemistry. We'll learn about this, sort of. Anyway, if I take 300 million meters per second and I square it, you know when you multiply stuff in scientific notation, you got to add the exponents. That gets you 9 and then 16 zeros. That's a lot. So let me explain how this works. This energy right here, when you take this deuterium and this tritium, tiny, tiny, tiny amount of mass is lost to energy when these fuse together to give you helium, like 0.00000 bunch of O's grams, okay? And when that happens, that tiny amount of mass that's converted to energy, that mass gets multiplied by the speed of light squared for the amount of energy you get out. And so the energy that you get out is enormous. This is how the sun works, but you have to have a lot of heat and pressure, like the heat and pressure at the core of the sun. And the sun is huge, right? Anyway, the sun loses, I think it's like 1,100 tons of mass a second to this. So that's why it's like keeping us nice and toasty, 93 million miles away. Isn't that interesting? So that's what the theory of relativity, that's what it's talking about, equals mc squared. Energy is equal to mass. And sometimes in these processes, mass gets turned to energy. And so you have this, mass can be energy, energy is mass, crazy, like quantum physics crap. But that's how that works. So if you want to get a job, you can make a new engine for a car, you can do fusion on Earth, or, I don't know, make plastic not kill people. There's some other jobs. I just kind of list them out as I feel like it, things I want to do when I grow up. So that's fusion. Tremendous energy is released because the mass that's lost to energy is multiplied by the speed of light squared. And like I said, we've made this happen on Earth for a little bit, other than making a bomb. Like scientists have tried to do this. But the energy you get out is less than what they had to put in. And I know there's some lasers involved and like a big core thing. And it's super hot, and they just can't make it happen. So, as far as the rest, I'd like to look it up. I really am curious. If we could control fusion and figure that out, this would be the answer to like everything. Like this would do, we would need nothing else. This would be enough. That would be kind of scary. So like I said earlier, meltdowns are where the radioactivity actually comes out of the containment building into the atmosphere. 3 Mile Island, this happened almost in 3 Mile Island. What happened in Pennsylvania is they drained the coolant water, the moderator, and all that stuff. That little building with the moderator and the control rods and everything, inside that containment building, everything was stored inside the containment building. So the radioactive stuff got out of that core, but it stayed in the containment building. So 3 Mile Island really scared everybody, but it should have made everybody feel better because even though the actual core leaked, the containment building kept it in. So nobody died, nobody got cancer, it was fine. Some people say, well, this person may have gotten cancer, but it was all right. So anyway, like I said, the containment building trapped it. So that's really like the only nuclear accident that we've had in the United States, which really ain't that bad. It was fine. So there's a picture, and like I said, these buildings right here, those are your cooling towers. People see them and they think that that's where the stuff comes out. That's where water comes out. Like this is those are your reactors right there. Those little guys. Okay, those are your cooling towers. Y'all watched me Simpson episodes, what it is. So anyway, 1986 with Chernobyl, that was definitely like the worst. It was due to human error. Like I said, people were undertrained in doing a test real quick. Anyway, 100,000 people were evacuated. 31 people died directly. Most of those people were working at the plant. The landscape in a 20-mile radius basically is still contaminated. And the fallout was carried around the northern hemisphere. It took the people in Sweden, I think it was over a week I bet you what had happened was, oh, I have a globe right there. This is, if you think about the circumference of the Earth, right? If you think about, like at the equator, right, that's pretty big, but as we go up here, I bet you that radiation went all the way around, back around to Sweden. That's what happened. And then at that high latitude, that's the only country that had like a nuclear power plant and actually gave crack. Because nobody does that. You know, you see what I'm saying? It went all the way around.
So anywhere else?
Yeah, because over here you got like Siberia, so you got like a train and Santa Claus, and then Alaska, there's no nuclear power plants, right? And then the top of Canada.
So were they not like
The people in Chernobyl, yeah,
but
but
like around the other,
I mean,
like in Sweden.
so you can be exposed to radiation and be fine, but the only people that would have sensors to pick up that minute trace would be a nuclear power plant, because nobody else is like checking for it, right? So that's why they picked it up. That's what happened. It went all around. That's why it took them so long. Because Russia was keeping on the down. They're like, nobody's got that. So, and then Sweden was like, So anyway, it was carried around much of the northern hemisphere. And the thing about this, people don't get it. They think that like nuclear radiation makes you like big and strong, like the Hulk, or like make sure kids have superpowers, or they make your kids
Like Chernobyl Diaries, that horror movie.
yeah, or like you get 4 arms. Like what actually happens with radiation is like way less sexy and interesting. You get thyroid cancer, okay? Sorry. So, yeah, you get thyroid cancer. So over time you develop thyroid cancer. And the short period you get ARS, which is acute radiation sickness. Acute radiation sickness.
It's not cute though.
It's acute. Acute means, so we're going to talk about that like tomorrow now. So acute means you're exposed for a short period of time. Chronic would be like you're exposed every day for your whole life. Acute would be like one time you're exposed. So acute radiation sickness. And kind of like a math, an acute angle is a little angle. You're exposed to it for a little bit of time. Okay. So anyway, the fallout was carried over most of the northern hemisphere. As far as it being strong enough for you not to be able to live there and it'd be dangerous, a 20-mile radius. But still, the winds picked it up and carried it around the Earth. I had to think about that for a minute. That was deep thought. And so here is the containment building. That's that. Yeah. So it exploded. It was totally gone. That's not funny. But there's actually some biologists, and this is kind of cool, like right around the power plant. I mean, the radiation is too high for people to live there. It would be dangerous, right? You could get thyroid cancer or superpowers. No, I'm just kidding. But scientists are going in and checking on it, and there's like whole packs of wolves that are just doing awesome. And so there's like a documentary called The Wolves of Chernobyl, which sounds like a cool, scary movie that you could go to the movies to see. But like ecologists are studying them, and they've done great because all the people left, which is sad. But anyway, you can go in and check in, study stuff, but they have to wear suits, and then they have to time it, and you can be exposed to so many rads. A rad is like a unit of radiation per amount of time, and it's safe, and so people have figured out what's okay, and they go in and study it, and so still radioactive, and it will be for like ever as far as on our time scale. But the wildlife around there is doing great. So, but they don't live as long as us. In Fukushima, if you guys remember, what ended up happening, let me kind of draw you some plate tectonics. So here is the Eurasian plate, and then here's the Pacific plate, and the Pacific plate is subducting, and when it does that, it melts and makes a volcano, and then that volcano that people live on is called Japan. So there's Japan. That looks good. I'll give it some water. It'll look better. I'm not good at drawing. There. So there's Japan. And I'll make it better. It has some volcanoes on it, right? That looks good. What I'm trying to tell you though is this plate right here is subducting, and what ends up happening when you have subduction happening in the ocean, this plate's trying to go under, and it gets stuck. And then eventually that pressure will get released and it'll go, hey Olivia. So pressure, and then it'll move. When it moves, that top plate kind of pops up, and when it pops up, the ocean water moves, and that's the tsunami. Okay, so made a huge earthquake. The earthquake killed way more people than the nuclear meltdown and all that. It was, I don't know, it wasn't very many. I want to say less than a dozen people, but the earthquake killed a bunch of people. But the actual power plant, that wasn't where the death and destruction came from. It was from the natural disaster, right? Sorry. Because this was right on the ocean, most of the radiation actually just went into the Pacific Ocean, and it was carried by the westerlies across the Pacific. What ended up happening was the cooling system didn't have electricity, and so that's what caused the overheating. So anyway, several explosions and fires happened. The radioactivity that was released was about 1/10 of Chernobyl. Most of it drifted into the Pacific. And then scientists did studies and found that some fish had radioactive levels that were unsafe in them. Pretty interesting. Thousands of people were evacuated. And then Japan kind of went into a freak-out mode about their nuclear for a minute. So there's their reactor. See them? And there's the tsunami coming for it. That's kind of terrifying. And if you look right here, like here's the coast of Japan, and it was right on the coast, and most of the radiation went out to the Pacific Ocean, carried by the westerlies. So that was, so both were westerlies, but didn't have to make it all the way around. And so off the coast of California, there was levels of radiation picked up. The biggest problem for radioactive stuff and nuclear is that we don't have anywhere to put the spent fuel. We don't have anywhere to store it. There's no long-term storage. Nobody wants that. That's definitely like a huge case of NIMBY, right? Not in my backyard. And so the U.S. plants, every bit of spent fuel that we have is held in temporary storage at the power plants and little pools of water. And you remember your summer work movie you had to watch? Yeah, and so those little tubs. I have a picture. I'll show you. Not tubs, but barrels of fuel. They're in these little cooling tanks right there. Turn the light off for a second. And so they're held there, temporary. But so let's say we had a place to put our nuclear fuel. Like we're gonna put this somewhere. Let's say there was a place in Nevada, like Yucca Mountain, right? Okay, we're gonna take our. We didn't ever do this, but the Senate had like. Started looking at it and maybe voting on it, but they never went through because, like, let's think about it. We're going to put our nuclear fuel in Nevada. We're going to take our nuclear waste from Georgia to Nevada. We're going to put it on a train and do that. Truck. Airplane. Right. So that's the issue. You see the problem? Nicole, are you awake? I know I'm enthralling right now. But anyway, it's unresolved, still unresolved today. And so all the waste is just sitting in these cooling places at the power plant. So after these are done and the fuel's done and the power plant has to be decommissioned, you have a huge mess on your hands. And you don't have that with coal. So anyway, Yucca Mountain, it was chosen because it was far away from people and the aquifer was like way below it. Little bit of tectonic activity, maybe an earthquake, but not too bad, like as far as risk factor goes. And it was dry, so they wouldn't have to worry about groundwater contamination. That's what was picked, but it never happened. So, we just don't know where to put it. People are scared of nuclear because of places like Chernobyl and Fukushima, but like I said, you have to realize there's 435 nuclear power plants. There's been 3 problems. One of them was contained in the containment building. One was because of dumb people. One was because of a huge earthquake. There's really not anything to be scared of. So they are expensive. They're very expensive to build. They're very expensive to run. They mostly go out of their budget, and they age. And once they age, you have to decommission them. That means you have to stop using them and then make it safe. And so that's a mess. It costs more. The government wants to. They have to subsidize the nuclear power to make it better. They stopped building plants. Like I said, the one at Plant Vogel is expanding. They're opening up another nuclear reactor there. So as far as the potential, it could come back up. It depends on what happens with this climate talk in Paris that's happening right now. So you can make it safer and less expensive. There's a group of people out of MIT that are actually trying to figure out how to use the waste spent fuel again, and they're doing a pretty good job, and they have a website. It was pretty neat. Jacob Johnson wants to be a nuclear physicist, and so like I looked at it with him a lot, and it was pretty cool. So So that's something you can do when you grow up if you want to. Like, I'm giving you career options. If you were planning on like being a businessman, sorry, you don't get to. You have to sign this. Okay. All right. So moving on from nuclear to biomass. Biomass is ultimately all organic material that came from the sun through photosynthesis. Oops. That sun part, though, you need to write that down because it's in the test. So ultimately from the sun. So anything like wood, charcoal, crops, manure, they're renewable. They don't release any carbon dioxide. Because if you burn these things, every bit of carbon dioxide that's released when you combust them was stored in them through photosynthesis. So it came out of the atmosphere, and when you burn it, you put it back in the atmosphere. Okay. So carbon released during burning, like I said, was originally from the atmosphere. So the difference between that and fossil fuels is when we burn fossil fuels, that carbon has been under the ground for millions of years. This was in the atmosphere recently. So anyway, most of this is coming from wood in developing countries being burned by people to heat their food in their homes. So that is the largest energy source in developing nations. That's why it's like 9% of the global energy economy, fuel wood, okay? Fuel wood and other traditional biomass sources, that's 75% of the renewable energy used worldwide. And these people are not using renewable energy because they want to help the earth. They're using it because they don't have any options. They don't have any methane or coal or natural gas. They would love to have a car and electricity. They don't have any, so they're burning wood. And that classifies as biomass. Like in the United States, our biomass, what we're doing is we're putting corn juice in our oil, and we're driving our cars around on it with ethanol. That's what I'm talking about, ethanol, corn juice, fermented corn juice. So anyway, we can burn wood, we can grow corn for ethanol, we can use biodiesel made from like soybean oil, which is cool. Crop residues, you can actually burn stuff like garbage or wood pulp. You can burn that with coal, and you can co-fire that and get a little bit more energy out of it, so that's pretty interesting. Anyway, biomass is only renewable if it's not over-harvested. So if you extract it faster than you let it grow back, then it's not renewable anymore. Right? So that's the definition of renewability. So anyway, that's that. So overall, worldwide, as far as biomass goes, this is what biomass means. That's what that means. Collecting fuel wood to heat your house and to cook your food. And that causes deforestation, causes lack of plant roots there to hold your soil in place, so you can cause desertification, which is, you know, where you have a lower productivity in your land. So like I was saying a second ago, you can actually, like some coal-fired power plants, they'll take plant crop residue, or they'll take wood pulp left over from wood mills, and they'll throw that in the furnace with coal, and they'll fire them together or burn them together. It's called coal firing. And some places will take garbage and do that, and so you get a little bit more energy out of it. So that's pretty cool, right? You should ask your dad about that. You can ask your dad if they co-fire anything, if they put anything in there with the coal. I'm sure they don't at Plant Bone, but they could somewhere. Be cool. Biopower, and biomass, like I said, you can burn things like garbage, you can burn things like crop residues. That's technically biomass, but as far as what we do with biomass, we make ethanol. That's what we do mostly. Biomass power increases efficiency and recycles waste product. So things like garbage and crop residues, that's waste products. So if you burn them, it's carbon neutral technically, and it reduces landfill space because you don't have to throw that in the landfill. It can support rural economies because you're growing the corn too, or the crops. So anyway, if we burn crops though, you start depleting your soil quality, so there's always the drawback, right? Ethanol is what we like to do in the United States with our corn. And so, but you don't have to use corn. Other countries like Brazil, that's not up there yet, but Brazil, they take sugar, and they use the sugar, and they ferment sugar, and that's what they do. You can use stuff like grasses, and you can ferment them. It doesn't have to be made from corn. The reason that we use corn in the United States is because we subsidize corn in the United States, and we have the good kind of soil for corn. So we have the resources for that. We can't grow sugar in the United States because we don't have the right climate, but sugar is way more efficient than corn. Anyway, we increase ethanol production by subsidizing it. 10% of every drop of gas that you put in your car ever now will be corn juice. And so that decreases what we have to import from foreign countries, and then we don't have to worry about political things and all that because it's domestic product. But if you think about how much corn that is for 10% of every bit of everybody's gas to be ethanol, that is astounding in my mind. That like blows my mind, right? That's a lot of corn. So when you see these numbers mixed with these little letters like E85, that means it's 85% ethanol and 15% gasoline. I told you a second ago that Brazil uses sugarcane, so there's that. Environmental scientists don't really like corn-based ethanol. The reason it's not like the best idea is because you still are going to have to grow the crops, and it's going to take up land. As more corn is used for ethanol, there's less used left for food. And so when NAFTA, the North American Free Trade Agreement, when it opened up trade with Mexico and Canada and made it a little bit easier, we flooded Mexico with our corn because it was so cheap because we subsidized it. And so Mexican farmers weren't able to keep up with their prices, and they went out of business, and they weren't able to grow the corn. That's why they started trying to immigrate to the United States, and then we're mean to them because we're like, you can't live here even though we mess up your whole food economy because we subsidize corn, which is ridiculous. Anyway, after we started using corn and ethanol and corn prices went up because of the increased demand, the book did that last sentence. I'm not going to say it, but I'll just let you read it real quick. That really happened. But people in Mexico weren't able to afford corn for their food. Anyway. That one slipped past me because I used to big PowerPoints. I hate PowerPoints. I would rather not make them, but that's messed up. Anyway, I need to make sure my little movie thing is still running. Let's see. I'm going to stop it. I'm going to stop this one.